Tonight we're going to talk about the largest star ever discovered, a star so enormous that if you could somehow transport it to where our sun sits, its glowing surface would stretch past the orbit of Saturn. The inner planets, Mercury, Venus, Earth, Mars, even the giant Jupiter, all of them would find themselves deep inside this star's outer atmosphere. By the end of tonight, you're going to see how we discovered a star barely holding itself together against its own light, why it sits at the edge of what nature allows, and how it reshaped everything we thought we knew about the true limits of stellar size. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. The year was 1990. Astronomer Charles Bruce Stephenson was conducting a systematic survey of the sky, searching for massive star clusters hidden in the dusty regions of our galaxy. He was looking in the constellation Scutum, a small faint constellation in the southern sky that sits right in the plane of the Milky Way. This region is crowded with stars, gas, and dust. It's one of those areas where the Milky Way appears particularly dense and bright, but also particularly obscured. All that dust makes it incredibly difficult to see what's actually there. Using infrared observations, which can penetrate dust better than visible light, Stephenson identified a cluster of stars roughly 19,000 light-years from Earth. It wasn't just any cluster. This cluster contained some of the most massive, most luminous stars he'd ever seen. Red supergiants, blue supergiants, stars pumping out hundreds of thousands of times more energy than our sun. The cluster became known as Stephenson 2, and for years it remained an interesting but relatively obscure object in astronomical catalogues, just another massive young cluster among thousands in our galaxy. But as infrared astronomy advanced through the 1990s and 2000s, as new space telescopes like Spitzer and Herschel came online, astronomers began to look at Stephenson 2 more carefully, and they started to realize something remarkable. One star in particular stood out. It was incredibly bright in the infrared, far brighter than it should be for a normal red supergiant. It was so bright that it suggested either the star was much closer than the rest of the cluster, which seemed unlikely, or it was extraordinarily large. They designated it Stephenson 218, the 18th star catalogued in the cluster. Nobody at the time realized they were looking at potentially the largest star ever discovered. That realization came later as astronomers began the painstaking work of actually measuring the star's properties. And here's where the challenge begins. How do you measure a star that's 19,000 light-years away? You can't send a probe there, you can't get a close-up image. You're working with photons of light that have been traveling through space for 19,000 years. Light that left this star around the time humans were still living in small hunter-gatherer groups, long before the pyramids were built, long before writing or agriculture or civilization. Those ancient photons finally arrive at our telescopes, and from them we have to reconstruct everything about this distant star, its temperature, its brightness, its size, its mass, its composition, all from light. The first step is measuring brightness. This is relatively straightforward. You point a telescope at the star, collect its light, and measure how much energy you're receiving. This gives you what's called apparent magnitude, how bright the star appears from Earth. For Stephenson 218, that apparent magnitude is fairly faint. You can't see it with the naked eye. Even through a small telescope, it's easily lost among thousands of other stars in that crowded region. But infrared telescopes revealed it's actually quite bright in the infrared, much brighter than in visible light. This makes sense for a cool star. Cool stars emit most of their energy as infrared radiation rather than visible light. Next, you need distance. Brightness alone doesn't tell you much because a faint nearby star and a bright distant star can appear equally bright from Earth. You need to know how far away the star is to calculate its actual intrinsic brightness, what astronomers call luminosity, For stars within a few thousand light years, astronomers can use parallax as Earth orbits the Sun. Nearby stars appear to shift position slightly against the background of more distant stars. By measuring this tiny shift, you can triangulate the distance using basic geometry, but parallax only works for relatively nearby stars. At 19,000 light-years, the shift is far too small to measure even with space telescopes, so astronomers use other methods. Since Stephenson 218 is part of a cluster, they can estimate the cluster's distance by studying the cluster as a whole, by measuring the properties of multiple stars in the cluster and comparing them to theoretical models. They can bracket the distance. Different methods give slightly different answers, which is why distance estimates for Stephenson 2 range from about 17,000 to 20,000 light-years. Let's use 19,000 as our best estimate. Now, with brightness and distance, you can calculate luminosity, how much total energy is the star actually emitting per second. The calculation revealed something stunning. Stephenson 218 has a luminosity roughly 440,000 times greater than our Sun. Every second, this star pumps out 440,000 times more energy than our Sun does. That's an almost incomprehensible amount of power, but luminosity alone doesn't tell you size. A small hot star can be very luminous. A large cool star can also be very luminous. To figure out size, you need temperature. This is where spectroscopy comes in. By splitting the star's light into a spectrum and analyzing which wavelengths are present, astronomers can determine the star's surface temperature. Different temperatures produce different spectral signatures. Hot stars show different absorption lines than cool stars. The spectrum of Stephenson 218 revealed something immediately obvious. This is a cool star, very cool. The surface temperature is only about 3600 Kelvin, which translates to about 6000 degrees Fahrenheit. That might sound hot, and it is by everyday standards, but it's actually cool for a star. Our Sun's surface is about 5770 Kelvin, over 10,000 degrees Fahrenheit. So Stephenson 218 is cooler than our Sun. This is why it glows red. Cool stars are red, hot stars are blue or white. The spectrum also revealed the presence of molecules in the star's atmosphere: titanium oxide, water vapor, carbon monoxide. These molecules can only exist at relatively cool temperatures. In hotter stars, they'd be ripped apart. Their presence confirmed this is a cool hypergiant. Now comes the crucial calculation. If you know how much total energy a star emits, its luminosity, and you know its surface temperature, you can calculate how large it must be. This uses a relationship called the Stefan-Boltzmann law. The law says that the total energy a star emits depends on two things: how hot its surface is. Hotter surfaces radiate more energy per unit area, and how much surface area it has. A cool star with enormous luminosity must have an enormous surface area to emit that much energy. When astronomers plugged in the numbers for Stephenson 218, the result was staggering. The star's radius came out to roughly 2,000 to 2,400 times the radius of our Sun. Let me put that in perspective. Our Sun's radius is about 433,000 miles. Multiply that by 2,000 and you get a radius of roughly 930 million miles. That's the distance from the star's center to its surface. The diameter of the distance across is about 1,860,000,000 miles. Stephenson 218 is the largest star ever discovered in the known universe. And now that you know how astronomers found it and measured it, let's explore what that actually means. 930 million miles in radius. That number is so large it's almost meaningless without context. So let's try to visualize it. If you could somehow replace our Sun with Stephenson 218, keeping everything else in the solar system the same, here's what would happen. The star's center would sit where the Sun's center currently sits. But instead of the Sun's surface being 433,000 miles from the center, Stephenson 218's surface would extend to approximately 10 astronomical units from the center. One astronomical unit is the distance from Earth to the Sun, about 93 million miles. so this star's surface would sit at 10 times that distance. Mercury orbits at about 0.4 astronomical units. It would be deep inside the star, completely engulfed. Venus at 0.7 astronomical units, also inside. Earth at 1 astronomical unit, the distance we use as our measuring stick, would be nowhere near the surface. We'd be deep within the star's outer envelope. Mars at 1.5 astronomical units inside. The asteroid belt between 2 and 3 astronomical units entirely contained within the star. Jupiter, the largest planet in our solar system, orbits at about 5.2 astronomical units. Even mighty Jupiter would find itself within the star's glowing atmosphere. Saturn, the ringed giant, orbits at about 9.5 astronomical units. Stephenson 2.18's surface would extend past Saturn's orbit. If you were standing on Saturn and looked up, you wouldn't see a bright point of light in the sky. You'd see a vast, dull red surface stretching across the entire sky, glowing like hot coals. You'd be inside the star. Only Uranus at 19 astronomical units and Neptune at 30 astronomical units would orbit outside the star's surface. The Kuiper belt, that region of icy objects beyond Neptune, would remain safely in the darkness beyond this cosmic giant. Now let's think about this in terms of volume. The volume of a sphere increases with the cube of its radius. If Stephenson 2.18's radius is about 2,000 times larger than the Sun's radius, its volume is 2,000 cubed. That's 2,000 times 2,000 times 2,000, about 10 billion. You could fit roughly 10 billion suns inside Stephenson 2.18, not 10, not 100, not a million, 10 billion. If our sun were a tennis ball, Stephenson 2.18 would be a sphere roughly 1,000 feet across, about the height of a 100-story skyscraper. If our sun were a marble, Stephenson 2.18 would be larger than a typical house. The scale is genuinely difficult for human brains to process. But here's where it gets even stranger. Despite being 10 billion times larger in volume, Stephenson 2.18 only contains about 12 to 16 times more mass than our Sun. How is that possible? The answer is density. Stephenson 2.18 is incredibly diffuse. Most of the star is near vacuum by terrestrial standards. The average density of the star is extraordinarily low, about 100 million times less dense than our Sun. The Sun has an average density of about 1.4 grams per cubic centimeter, slightly higher than water. Stephenson 2.18's average density is about 0.000014 grams per cubic centimeter. That's 14 millionths of a gram per cubic centimeter. For comparison, the best vacuum we can create in laboratories on Earth is about 1 trillionth of a gram per cubic centimeter. So even the star's average density is thousands of times higher than laboratory vacuum, but it's incredibly low by stellar standards. The core would be much denser, perhaps approaching or exceeding the Sun's core density, but the outer envelope is extraordinarily thin, almost nothing by any terrestrial standard. This extreme diffuseness is one of the defining characteristics of hypergiants. These stars have swollen to such enormous sizes that their outer layers are barely held together by gravity. In fact, they're constantly losing mass. Powerful stellar winds blow material away from the surface at rates that would horrify any engineer trying to build a stable system. Some estimates suggest Stephenson 2.18 might be losing mass at a rate of about 1/10,000th of a solar mass per year. That might not sound like much, but over 1 million years, that's 100 solar masses, more mass than many entire stars contain. Let's talk about what it would be like to visit this star, hypothetically. Imagine you're in a spacecraft approaching Stephenson 2.18 from a distance of several astronomical units. The star would dominate your entire field of view. It wouldn't look like a point of light anymore. It would look like a vast glowing wall filling the sky. As you got closer, the star's reddish color would become more apparent. This is a cool star by stellar standards, glowing red-orange rather than white or blue. The surface would be dim compared to our Sun, despite being 440,000 times more luminous overall. The light is spread out over such an enormous surface area that the surface brightness is actually quite low. If you could somehow stand on a platform at the star's surface and look around, the local area wouldn't be blindingly bright. It would glow dully like hot coals in a fireplace. You could possibly look directly at the surface without your eyes being instantly destroyed, though the infrared radiation would still kill you quickly. The real danger wouldn't be visible light, it would be heat. Even though the surface temperature is only about 3600 Kelvin, the sheer amount of radiation being emitted would cook anything nearby. At the distance of Earth's orbit from the center of this star, assuming you could somehow survive inside the star's outer envelope, the temperature would be several thousand degrees. Everything would be plasma. No solid matter could exist. As you approach the core, temperatures would climb into the millions of degrees. The core of Stephenson 218, where fusion is taking place, likely reaches temperatures of several hundred million degrees Kelvin. At those temperatures, matter breaks down into bare nuclei and free electrons. The pressure is millions of times greater than Earth's atmospheric pressure. Nothing remotely like a physical structure could exist there. It's a realm of pure energy and fundamental particles. Now, one of the most remarkable things about Stephenson 218 is just how temporary its existence is. Stars like this are rare, not just in space but in time. Our Sun has a total lifespan of about 10 billion years. It's currently about 4.6 billion years old, roughly halfway through its life. It will continue fusing hydrogen for another 5 billion years or so before it runs out of fuel and swells into a red giant. Stephenson 218, by contrast, will live for maybe 20 million years total, maybe less. It might have already exploded as a supernova, and we just don't know it yet, because the light from that explosion is still traveling toward us. Remember, the star is 19,000 light years away. What we see today is what the star looked like 19,000 years ago. If it exploded 10,000 years ago, we wouldn't know for another 9,000 years. This timescale asymmetry is one of the strange consequences of looking at objects light years away. You're always looking into the past. When Stephenson 218 finally does explode, and it will, the explosion will be spectacular. Hypergiants like this are thought to end their lives in supernovae, possibly even hypernovae, which are supernovae on steroids. A hypernova releases more energy than a typical supernova, possibly enough to create a gamma-ray burst. Gamma-ray bursts are the most energetic events in the universe aside from the Big Bang. They release more energy in a few seconds than our Sun will emit in its entire 10 billion year lifetime. If Stephenson 218 produces a gamma-ray burst when it dies, and if that burst is aimed in our direction, it could be visible from Earth even at 19,000 light-years away. It would appear as an incredibly bright point of light in the constellation Scutum, potentially visible during the day for a short period. But we don't need to worry about danger. At 19,000 light-years, the radiation would be dispersed and absorbed by interstellar material long before reaching Earth. We'd be safe. We'd just get a spectacular light show. The supernova remnant would expand outward at a significant fraction of the speed of light, plowing into surrounding gas and creating a glowing nebula. That nebula would remain visible for thousands of years, slowly fading as it cooled and dispersed. The core would collapse, given the star's estimated mass, somewhere between 12 and 16 solar masses. It's right on the borderline between forming a neutron star or a black hole. Neutron stars form from stars with cores between about 1.4 and 3 solar masses. Above that, the core collapses all the way down into a black hole. Stephenson 218's fate depends on how much mass it's lost through stellar winds. If it's shed enough mass, the remaining core might form a neutron star. If it's retained most of its mass, it could form a black hole. Either way, the hypergiant will be gone, replaced by a compact remnant. Let's put Stephenson 218 into context with other extreme stars to give you a sense of just how unusual it is. Our Sun is a G-type main sequence star, fairly average in size and mass. Most stars in the galaxy are actually smaller and cooler than the Sun. Red dwarfs, the smallest stars that can sustain fusion, make up about 70% of all stars. A typical red dwarf might have a radius of only 10 to 20% of the Sun's radius, mass perhaps 10 to 50% of the Sun's mass. Red dwarfs are tiny, dim, and incredibly long-lived. The smallest red dwarfs will burn for trillions of years. At the other extreme, you have blue supergiants and hypergiants. These are massive, hot, and incredibly luminous. Rigel, the bright blue star in Orion's foot, is a blue supergiant with a radius about 79 times the Sun's radius. It's enormous compared to the Sun, but minuscule compared to Stephenson 218. Then there are red supergiants, cooler stars that have swollen to enormous sizes. Betelgeuse, the red star in Orion's shoulder, is perhaps the most famous red supergiant. Its radius varies because the star pulsates, but estimates put it somewhere around 764 solar radii. That's huge. If you place Betelgeuse where the Sun is, its surface would extend past the orbit of Mars, possibly reaching the asteroid belt. But Stephenson 218 is still nearly 3 times larger. Antares, another famous red supergiant in the constellation Scorpius, has a radius of about 680 solar radii. VV Cephei, one of the largest known red supergiants, has a radius around 1500 solar radii, still smaller than Stephenson 218. Scutum, which was thought for a time to be the largest star, currently has a measured radius of about 755 solar radii, though earlier estimates were much higher. The point is, even among the largest stars, Stephenson 218 stands out. It's in a class of its own now. There's an important caveat to mention. Measuring stellar radii, especially for distant red hypergiants, is extraordinarily difficult. These stars are often surrounded by thick clouds of dust ejected from their own surfaces. The dust absorbs and scatters light, making it hard to determine where the star's surface actually is. Additionally, many of these stars pulsate, expanding and contracting over months or years. Their size isn't constant. Stephenson 218 might be larger at some times and smaller at others. The measurements we have are snapshots, and they come with error bars. The radius estimate of 2000 to 2400 solar radii is a range, not a precise number. Future observations with better instruments might refine this. It's possible that another star could be found to be larger. It's possible that improved measurements could show Stephenson 218 is smaller than currently thought, but based on the best data available right now, it's the largest. Let's talk about the cluster this star calls home. Stephenson 2 is an open cluster, a group of stars that form together from the same molecular cloud. The cluster is young by stellar standards, only about 20 million years old. It contains some of the most massive stars in the galaxy, including multiple red supergiants and hypergiants. The cluster's location in the galactic plane means it's embedded in dense star-forming regions. There's active star formation happening nearby. This environment is rich in gas and dust, the raw materials for making stars. Stephenson 2 is thought to be one of the most massive young clusters in the Milky Way. It contains an estimated 50,000 to 100,000 solar masses worth of stars. Some of the other notable members include Stephenson 2-3, another red hypergiant, and Stephenson 2-7, also a red supergiant. These are all massive stars in late stages of evolution. Within a few million years, many of them will explode as supernovae. The cluster will eventually be torn apart by these explosions and by gravitational interactions. Young clusters like Stephenson 2 don't last long. Over tens of millions of years, the stars drift apart, dispersing into the general galactic population. So the cluster we see today is a temporary association, a snapshot of a brief moment in the galaxy's history, when a bunch of massive stars happen to be in the same place. In 100 million years, Stephenson 2 as a cluster won't exist anymore. Its stars will be scattered across a large region of the galaxy, but the legacy of these stars will remain. When they explode, they'll enrich the interstellar medium with heavy elements. Carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements created in their cores and during their supernova explosions. These elements will become part of new clouds of gas and dust. Those clouds will collapse to form new stars and planets. The atoms in your body, the iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created in stars. Most of it was created in stars like Stephenson 218. Massive stars are the universe's element factories. They're where the complexity of chemistry is built. Without massive stars, the universe would consist only of hydrogen and helium. No rocky planets, no water, no life. Stars like Stephenson 218 are rare, but they're crucial to the universe's ability to create complexity. They live fast, die young, and in their death throes, they seed the cosmos with the building blocks of future worlds. Now let's address a common question. Could life exist on a planet orbiting a star like Stephenson 218? The short answer is no, not in any way we'd recognize. First, the star's lifetime is far too short. Life as we know it took billions of years to develop on Earth. Simple single-celled organisms appeared about 3.8 billion years ago. Complex multicellular life didn't appear until about 600 million years ago. Intelligent life is even more recent. A star like Stephenson 218 will only live for about 20 million years total. That's not remotely enough time for life to evolve from chemistry. Second, the star's environment is incredibly hostile. Even if a planet somehow formed in orbit around this star before it became a hypergiant, which is unlikely, the planet would be subjected to intense radiation. The star's luminosity varies as it pulsates. The stellar wind would be stripping away any atmosphere. When the star swelled into a hypergiant, it would have engulfed any planets that were in close orbits. Planets that started out in the habitable zone would have been vaporized as the star expanded. Third, massive stars like this emit a lot of ultraviolet radiation and X-rays. This high-energy radiation would break apart molecules, making it extremely difficult for complex chemistry to survive on any nearby planet. The only way a planet could possibly be habitable around a star like this would be if it orbited very far away, many astronomical units out, well beyond the star's swollen envelope. But even then, the star's lifetime would be too short and the radiation environment too harsh. So no, planets around hypergiants are not good places to look for life as far as we understand it. Needs stable conditions over long time scales. It needs a star that will shine steadily for billions of years, providing consistent energy. It needs liquid water, organic molecules, and protection from radiation. Hypergiants provide none of these things. They're spectacular objects, crucial to the chemical evolution of the universe, but not homes for life. The best places to look for life are around stars like the Sun, medium-mass stars that burn steadily for billions of years, providing stable energy output over geological timescales, or possibly around red dwarfs, the smallest stars which burn for trillions of years, though they have their own challenges with flares and tidal locking. Hypergiants are fascinating, but they're factories, not nurseries. They make the elements needed for life, but they don't host it. Here's another angle to consider. What if you could harness the energy of a star like Stephenson 218? The concept of a Dyson sphere, a megastructure that surrounds a star to capture all its energy, was proposed by physicist Freeman Dyson in 1960. The idea is that an advanced civilization could build a swarm of solar collectors orbiting a star, capturing a significant fraction of its energy output. For a star like the Sun, this would provide enormous energy, far more than humanity currently uses. For a star like Stephenson 218, the energy available would be staggering. Remember, this star outputs 440,000 times more energy than the Sun. If you could capture even a small fraction of that energy, you'd have power on a scale almost beyond comprehension. But building a Dyson sphere around Stephenson 218 would be impractical for several reasons. First, the star's lifespan is too short. By the time you built the megastructure, the star would be nearing the end of its life. You'd invest enormous resources into a project that would only last a few million years at most before the star exploded and destroyed everything. Second, the star is so large that the amount of material needed to build a structure around it would be prohibitive. To build a solid shell around a star with a radius of 2 billion miles would require more material than exists in the entire solar system. You'd need to dismantle thousands of planetary systems to gather enough raw materials. Third, the star's intense radiation and violent stellar winds would make construction and maintenance nearly impossible. Any structure would be subjected to constant bombardment of high-energy particles and radiation. It would need to be incredibly robust, far beyond anything we can currently imagine building. A more practical approach would be to build your Dyson sphere around a stable, long-lived star, a star like the Sun, or even a red dwarf, stars that will shine steadily for billions of years, providing reliable energy for a civilization's entire history. Stephenson 218 is impressive, but it's not a good candidate for long-term energy harvesting. It's too unstable, too short-lived, and too violent. Now let's zoom out and think about the role of stars like Stephenson 218 in the galaxy's evolution. The Milky Way has been forming stars for over 13 billion years. During that time, countless generations of stars have been born, lived, and died. The first stars, called population 3 stars, formed from pure hydrogen and helium. No heavy elements existed yet, because heavy elements are only created in stars. These first stars were likely very massive, burning hot and fast, exploding as supernovae after just a few million years. Their explosions seeded the universe with the first heavy elements: carbon, oxygen, nitrogen, silicon, magnesium, iron. These elements mixed with the remaining hydrogen and helium, creating chemically enriched gas clouds. The next generation of stars, population 2 stars, formed from this slightly enriched material. They contained a small fraction of heavy elements, enough to allow more complex chemistry in any surrounding material. Our Sun is a population I star, part of the most recent generation. It formed about 4.6 billion years ago from gas that had already been enriched by multiple previous generations of stars. The solar system's planets, including Earth, formed from material that contained about 2% heavy elements by mass. That 2% came entirely from previous stars. Stars like Stephenson 218 are part of this ongoing cycle. When it explodes, it will scatter heavy elements into the interstellar medium. Those elements will eventually become part of new stars and planets. This is how the galaxy gradually becomes more metal-rich over time. Astronomers call any element heavier than helium a metal, even though most of them aren't metals in the chemistry sense. When they say a star is metal-rich, they mean it contains a higher fraction of elements heavier than helium. Metal-rich stars are younger. They formed from gas that had been processed through multiple earlier generations of stars. Metal-poor stars are older. They formed from gas that had been less enriched. Stephenson 218 is a young metal-rich star. It formed from gas that already contained significant amounts of heavy elements from previous stellar generations. And when it dies, it will add even more heavy elements to the mix, contributing to the galaxy's ongoing chemical evolution. This process is why the universe is able to create complex structures. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. Everything else, every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in Earth's core, all of it was made in stars. Most of it was made in massive stars like Stephenson 218. These stars are the universe's alchemists. They take simple elements and forge them into complex ones. They live briefly but brilliantly, and in their death they enrich the cosmos. Without them, the universe would be a far simpler, far less interesting place. Let's think about observation. How do we actually study a star like Stephenson 218? It's not like we can send a probe there at 19,000 light years away. Even traveling at the speed of light, it would take 19,000 years to reach it. No spacecraft we've built could make that journey. Voyager 1, our fastest and most distant probe, has been traveling for over 47 years and has only covered about 0.002 light years. At that rate, it would take millions of years to reach Stephenson 2 to 18, so we study it from a distance using telescopes. We collect light from the star, split that light into a spectrum, and analyze the patterns. Different elements absorb and emit light at specific wavelengths. By studying which wavelengths are present or absent, we can determine the star's composition, temperature, velocity, and other properties. We can also measure the star's brightness over time to see if it varies. Many red hypergiants are variable stars, meaning their brightness changes periodically. This variation is caused by pulsations. The star expands and contracts, changing its size and temperature, and therefore its brightness. By tracking these variations, we can learn about the star's structure and dynamics. Some observations are done in visible light, but many are done in infrared. Stephenson 218 is heavily obscured by dust, both in the cluster itself and in the interstellar medium between us and the star. Infrared light penetrates dust better than visible light, allowing us to see through the obscuration. Radio observations can also be useful. Stars emit radio waves, and studying those waves can reveal information about stellar winds, magnetic fields, and other phenomena. Interferometry, combining light from multiple telescopes to act as a single larger telescope, can achieve higher resolution. This technique has been used to directly measure the sizes of some nearby giant stars. For stars as distant as Stephenson 218, interferometry is challenging but potentially possible with large enough baselines. Most of what we know comes from photometry and spectroscopy. Photometry is measuring brightness, spectroscopy is measuring the spectrum. Together they give us a remarkably complete picture of a star's properties. We can determine its temperature, luminosity, composition, mass, radius, age, and evolutionary state, all from light collected across 19,000 light-years of space. It's a testament to human ingenuity and the power of physics that we can learn so much about an object we'll never physically reach. Here's a thought. How many stars like Stephenson 218 exist in the galaxy? The answer is not many. Hypergiants are exceedingly rare. Out of the hundreds of billions of stars in the Milky Way, only a few dozen hypergiants have been identified. This rarity is partly because hypergiants are genuinely uncommon, and partly because they're hard to find. They're often obscured by dust, located in distant or crowded regions, and they don't live long. Even if the galaxy produces a hypergiant every few thousand years, each one only lasts for a few million years. That means at any given time there might only be a few thousand of them in existence across the entire galaxy, and most of those are too distant or too obscured for us to detect. The ones we have found are mostly nearby, within a few tens of thousands of light-years. Stephenson 218 at 19,000 light-years is one of the more distant ones we've studied in detail. There are almost certainly other hypergiants farther away, hidden from us by distance and dust. We'll probably discover more as our instruments improve and our surveys cover more of the sky, but hypergiants will always be rare. They represent a brief, extreme phase in the life of the most massive stars. Most stars never become hypergiants. They're not massive enough. Only stars with initial masses above roughly 20 to 25 solar masses can evolve into hypergiants, and even then, only under certain conditions. Most massive stars explode as supernovae while they're still blue supergiants. Only some evolve into red supergiants, and only a fraction of those become hypergiants. So Stephenson 218 is a rare object, a glimpse at the extreme end of stellar evolution, a star that's pushed the limits of size to the breaking point. Let's return to that visualization we started with. Imagine standing on Earth and looking up at the night sky. Now imagine that instead of the sun, Stephenson 218 sits at the center of our solar system. The sky would be utterly transformed. During the day, you wouldn't see a bright point of light overhead. You'd see a vast, dull red disk covering a huge portion of the sky. The star's surface would be close enough that it would appear as a disk, not a point, and because you'd be inside the star's outer envelope, the sky would be filled with glowing gas. Of course, Earth wouldn't exist in this scenario. The planet would have been vaporized when the star expanded. But if somehow you could have a platform floating in space at the distance where Earth normally orbits, say 1 astronomical unit from the center, you'd be deep inside the star's atmosphere. The temperature would be thousands of degrees, the pressure would be immense, you'd be surrounded by glowing plasma. Looking outward, you'd see a gradually brightening glow toward the star's core and a dimming glow toward the surface. There would be no sharp boundaries, no clear sense of up or down, just an endless sea of glowing gas in all directions. It's a vision of hell in some sense, a place utterly hostile to anything resembling life or structure, and yet it's also a place of creation. This is where heavy elements are being forged, where the raw materials for future planets and future life are being created. The same processes that make this environment lethal are the processes that make the universe capable of complexity: fusion in the core, convection in the envelope, mass loss through stellar winds, and eventually a supernova that will scatter enriched material across light years of space. These aren't just destructive processes, they're constructive. They are how the universe builds the chemical foundation for everything that comes after. Stephenson 218 will not last. Within a few million years, possibly within the next million years, it will explode. The explosion will be visible from Earth, a bright new star appearing in the constellation Scutum. It will outshine most of the stars in the night sky for weeks or months before, gradually fading. The remnant will expand outward, eventually forming a nebula that might be visible for thousands of years, and then slowly the nebula will disperse. The elements created in the star and in the supernova will mix with the interstellar medium. New stars will form from that enriched material. Some of those stars will have planets, some of those planets might develop life, and if they do, that life will owe its existence in part to Stephenson 218. The carbon in its molecules, the oxygen in its atmosphere, the iron in its core, all of it will have been created in stars like this one. This is the legacy of hypergiants. They don't leave behind stable systems or long-lived structures. They leave behind enriched material, the seeds of future complexity. Now, before we close, let's think about what Stephenson 218 means for our understanding of the universe. This star challenges our models of stellar evolution. Stars this large shouldn't be stable, yet they exist. They should blow themselves apart under their own radiation pressure, yet they hold together, at least for a while. Studying stars like this helps refine our theories. It shows us the extremes, the edge cases where our models are tested. Every observation of a hypergiant gives us more data, more constraints on the physics, and there's still a lot we don't understand. We don't fully understand the mass loss mechanisms. How exactly does a hypergiant shed mass through stellar winds? What drives those winds? How much mass is lost over the star's lifetime? We don't fully understand the internal structure. What's happening in the core? How does convection work in a star this large and this diffuse? Are there layers or shells of different compositions? We don't fully understand the end state. Will Stephenson 218 explode as a normal supernova, or will it produce something more exotic? Could it collapse directly into a black hole without a visible explosion? These are open questions, and the only way to answer them is to keep observing, keep building better instruments, keep refining our models. Stephenson 218 is one data point in a larger effort to understand how stars work. But it's an important data point because it represents the extreme, and understanding the extremes helps us understand the full range of behavior. If we only studied stars like the Sun, we'd have a very incomplete picture. We need to study the smallest stars, the largest stars, the hottest, the coolest, the youngest, the oldest. Every type of star teaches us something different. Hypergiants teach us about the limits. How large can a star become? How luminous, how unstable? What happens when you push the physics to the breaking point? Stephenson 218 is an answer to some of those questions and a source of new questions for others. Let me tell you more about what makes red hypergiants specifically so fascinating. These stars exist in a very narrow evolutionary phase. They are massive stars that have exhausted the hydrogen in their cores and moved on to fusing heavier elements, but they haven't yet reached the final stages that lead to supernova. They're in transition, and that transition creates unique conditions. The core of a red hypergiant is contracting and heating up as it fuses helium into carbon and oxygen. This contraction releases gravitational energy, which heats the surrounding layers. Those outer layers respond by expanding dramatically. It's counterintuitive, but it's how stellar physics works. A contracting core leads to an expanding envelope. The envelope expands so much that it cools down significantly. The surface temperature drops from tens of thousands of degrees for a main sequence massive star to just a few thousand degrees for a red hypergiant. This cooling causes the star to glow red instead of blue or white, but despite the cooler surface, the total energy output actually increases. The star becomes more luminous because the surface area is so enormously larger. Think about it this way. A small hot piece of metal radiates a certain amount of energy. A huge warm piece of metal might radiate much more total energy, even though each square inch is cooler. That's what's happening with red hypergiants. The surface is cooler per unit area, but there's so much more surface area that the total output is staggering. Now, one of the most interesting things about these stars is their instability. Red hypergiants are not stable objects. They pulsate, they vary in brightness, they shed mass erratically. The outer envelope is so loosely bound that it's constantly being lost to space. Powerful stellar winds carry away material at rates that would horrify any engineer trying to build a stable system. Some estimates suggest Stephenson 2 to 18 might be losing mass at a rate of about 1/10,000th of a solar mass per year. That might not sound like much, but over 1,000,000 years, that's 100 solar masses, more mass than many entire stars contain. This mass loss has profound consequences. It means the star is constantly getting smaller, losing its outer layers. It also means the space around the star is filled with previously ejected material. This creates a circumstellar envelope, a cloud of gas and dust surrounding the star. When we observe Stephenson 218, we're not just seeing the star itself, we're seeing the star plus this surrounding material. That makes precise measurements even more difficult because you have to account for the contribution from the circumstellar material. Some of that material is being pushed away by radiation pressure. Photons from the star hit dust grains and atoms in the envelope, transferring momentum. This pressure pushes material outward, creating a wind, but it's not a smooth, steady wind. It's clumpy, variable, and irregular. Observations show that red hypergiants can have large-scale convection cells on their surfaces. These are rising and falling currents of hot and cool gas, similar to the convection you see in boiling water, but on an unimaginably larger scale. A single convection cell might be larger than the entire orbit of Earth around the Sun. These convection cells create hot spots and cool spots on the star's surface. As the star rotates, which it does, albeit slowly, these spots move in and out of view. This causes variations in brightness that we can measure from Earth. By studying these variations, astronomers can learn about the star's rotation rate, its surface structure, and the physics of convection at extreme scales. Another source of variability comes from pulsations. The star expands and contracts over periods of months or years. During expansion, the surface moves outward, the star gets larger, and the temperature drops slightly. During contraction, the opposite happens. These pulsations are driven by the Kappa mechanism, a feedback loop where increased opacity in the star's outer layers causes them to absorb more radiation, heat up, expand, then cool and contract again. It's a natural oscillation like a spring bouncing up and down. For Stephenson 218, these pulsations might change the star's radius by 10 or 20% over the course of a year or two. That means the star could vary from about 1800 solar radii to 2200 solar radii over a pulsation cycle. Measuring these variations helps astronomers understand the star's internal structure, because the pulsation period depends on the star's mass, radius, and internal density distribution. Now let's think about the star's magnetic field. Most stars have magnetic fields generated by dynamo processes in their interiors. The Sun has a magnetic field that creates sunspots, flares, and coronal mass ejections. Red hypergiants likely have magnetic fields too, though they're much harder to measure because the stars are so distant. The magnetic field in a red hypergiant would be shaped by the star's rotation and convection. As convective cells rise and fall, they drag magnetic field lines with them, creating complex, tangled magnetic structures. These magnetic fields might play a role in driving mass loss. They could channel material away from the star along magnetic field lines, similar to how the Sun's magnetic field channels solar wind. They might also create hot spots where magnetic field lines concentrate energy, heating localized regions of the star's atmosphere. These hot spots could contribute to the X-ray emission that's been detected from some red hypergiants. X-rays from a cool star might seem contradictory, but magnetic activity can create small regions of extremely hot plasma even in an otherwise cool stellar atmosphere. The study of red hypergiant magnetic fields is an active area of research. Better instruments, particularly spectropolarimeters, that can measure the polarization of light caused by magnetic fields, are helping astronomers map these fields. Each new observation adds to our understanding of how these extreme stars work. Let's talk about some specific comparisons to help you really grasp the scale we're dealing with. Stephenson 218's radius is approximately 930 million miles. Let's break that down into different units to see it from multiple angles. In astronomical units, it's about 10 astronomical units. Remember, 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. So this star's radius alone is 10 times the Earth-Sun distance. Its diameter, therefore, is about 20 astronomical units. Neptune, the outermost planet in our solar system, orbits at about 30 astronomical units from the Sun. If you placed Stephenson 218 at the center of our solar system, its surface would extend well beyond Neptune's orbit. Actually, no, let me correct that. The star's diameter is 20 astronomical units, so its radius extends to 10 astronomical units. Saturn orbits at about 9.5 astronomical units, so the star's surface would extend just past Saturn's orbit, not Neptune's. Neptune would still be outside. Pluto, the dwarf planet, orbits at an average distance of about 39 astronomical units. Pluto would be safely outside the star. The Kuiper belt, the region of icy objects beyond Neptune, starts at around 30 astronomical units and extends to about 50 astronomical units. The Kuiper belt would remain outside the star's surface. Only objects within about 10 astronomical units would be engulfed. Now let's think about time. Light travels at roughly 186,000 miles per second. In 1 second, light can circle Earth's equator about 7.5 times. Light takes about 8 minutes and 20 seconds to travel from the Sun to Earth. How long would it take light to cross Stephenson 218's diameter? The diameter is about 1,860,000,000 miles. Light travels 186,000 miles per second. Divide 1,860,000,000 by 186,000 and you get approximately 10,000 seconds. That's about 2 hours and 47 minutes. Light would take about 2 hours and 47 minutes to travel from one side of Stephenson 218 to the other. Compare that to the Sun, where light takes only about 4.6 seconds to cross the diameter, or Earth, where light takes about 0.042 seconds to cross. This star is so large that light, the fastest thing in the universe, takes nearly 3 hours to cross it. If you were somehow at the center of Stephenson 218 and you sent a light signal to the surface, it would take about 1 hour and 24 minutes to get there. By that time, conditions might have changed significantly in the star's dynamic outer layers. Another comparison involves mass. We've said Stephenson 218 contains about 12 to 16 times the Sun's mass. The Sun's mass is approximately 2 times 10 to the 30th kilograms. That's a 2 followed by 30 zeros. It's about 330,000 times the mass of Earth. So Stephenson 218 contains somewhere between 24 and 32 times 10 to the 30th kilograms. That's equivalent to somewhere between 4 million and 5.3 million Earths. But remember, this mass is spread out over a volume 10 billion times larger than the Sun. The average density is therefore about 1 billion times lower than the Sun. The Sun has an average density of about 1.4 grams per cubic centimeter, slightly higher than water. Stephenson 218's average density is about 0.000001 grams per cubic centimeter. That's 14 millionths of a gram per cubic centimeter. For comparison, the best vacuum we can create in laboratories on Earth is about 1 trillionth of a gram per cubic centimeter. So even the star's average density is thousands of times higher than laboratory vacuum, but it's incredibly low by stellar standards. The core would be much denser, perhaps approaching or exceeding the Sun's core density, but the outer envelope is extraordinarily thin, almost nothing by any terrestrial standard. Now let's explore the historical context of red hypergiant discovery. For most of human history, stars were thought to be unchanging, eternal points of light. The ancient Greeks called them the fixed stars to distinguish them from the wandering stars, the planets. It wasn't until the Renaissance that astronomers began to realize stars could change. In 1572, Tycho Brahe observed a new star that appeared in the constellation Cassiopeia. It was brighter than Venus at its peak and visible during the day. This was a supernova, though that term wouldn't be coined for centuries. In 1604, Johannes Kepler observed another supernova in Ophiuchus. These observations challenged the idea that the heavens were unchanging, but the nature of stars themselves remained mysterious. Were they other suns like ours? Were they different types of objects? How far away were they? These questions weren't answered until the 19th and 20th centuries. The development of spectroscopy in the mid-1800s allowed astronomers to analyze starlight in detail. By splitting light into its component colors, scientists could identify which elements were present in a star's atmosphere. Different elements absorb and emit light at specific wavelengths, creating distinctive patterns. This technique revealed that stars are made mostly of hydrogen and helium, the same elements found on Earth but in different proportions. It also revealed that stars come in different temperatures. Hot stars are blue, cool stars are red. In the early 1900s, astronomers Ejnar Hertzsprung and Henry Norris Russell independently developed what's now called the Hertzsprung-Russell diagram. This is a graph that plots stars' luminosity versus temperature. When you plot thousands of stars on this diagram, patterns emerge. Most stars fall along a diagonal band called the main sequence where our Sun sits, but some stars lie off the main sequence. These are giants and supergiants, stars that are much more luminous than main sequence stars of the same temperature. Red giants and red supergiants occupy the upper right corner of the diagram. High luminosity but cool temperature. As telescopes improved and surveys catalogued more stars, astronomers found that the red giant region extends to extraordinarily high luminosities. Some stars are so luminous they dwarf anything else in their vicinity. These ultra-luminous cool stars were eventually classified as hypergiants. The term hypergiant was coined to distinguish them from regular supergiants. They're not just bigger, they're in a completely different category of extremity. Early examples included stars like VV Cephei, discovered in the 1930s to be a red supergiant with an enormous radius. Mu Cephei, also called Herschel's garnet star, because of its deep red color, was another early known red supergiant. V Canis Majoris was long thought to be the largest star known, with radius estimates in the 1990s suggesting it might be up to 2,800 solar radii. Later measurements revised that estimate downward to about 1420 solar radii, still enormous but not quite as large as originally thought. This pattern of revising estimates is common in astronomy. As instruments improve and techniques get better, measurements become more accurate. Early estimates often have large uncertainties, and sometimes the true value turns out to be different from initial estimates. Scutum was another contender for the largest star, discovered in the 1860s. It wasn't until modern infrared observations that its true size was appreciated. Initial estimates suggested radii as high as 1900 solar radii. Current estimates are lower, around 755 solar radii. Stephenson 218 entered this competition relatively recently. The cluster was discovered in 1990, but detailed studies of individual stars within it came later. It wasn't until the 2000s and 2010s that high-resolution infrared observations allowed astronomers to measure the properties of stars within the cluster accurately. Stephenson 218 emerged as a strong candidate for the largest known star based on these observations. Its large radius, combined with relatively high confidence in the measurements, puts it at or near the top of the list. But the competition continues. Astronomy is an ongoing process. New stars are discovered, old measurements are refined, and the rankings change. What we can say is that Stephenson 218 is among the largest stars ever found, and quite possibly the largest. Future observations will continue to refine our understanding. Thanks for joining me on this exploration of the largest star in the universe. If you found this journey as fascinating as I did, consider liking the video or subscribing to the channel. It helps these stories reach more people who share our curiosity about the cosmos. And remember, the next time you look up at the night sky, somewhere out there in the constellation Scutum, invisible to your eyes but real nonetheless, Stephenson 218 is shining, a cosmic giant living fast, burning bright, and preparing for its final magnificent act.